Okay, question 8. It says a learner was asked to build a functioning galvanic cell. Okay, the following are provided: a magnesium rod, a copper rod, um, 1 mole per decimeter cube of sodium carbonate solution, magnesium sulfate solution, copper sulfate solution. Okay, now let's see what they ask us. Okay. Then say a partial label galvanic build cell built by the learner shown here. So we have that. If electrons move from the left electrode to the right electrode, label the part thereof. So it means here, in whatever reaction is here, electrons will be taken away, and then here, because electrons move from here to that point, it means this one will be something plus electrons to produce whatever. So but we need to choose between magnesium rod as well as copper rod. Which one is which, right? And can you see we have to use copper that has 2 plus, okay, because due to copper 2 here. Okay, so we go to our table of standard reduction. We compare between, actually let me do this. We compare between magnesium 2 plus, okay, as well as copper 2 plus. That results in a pure copper. Okay, copper 2 plus, that results in a pure copper like that. Can you see CO? Not CO plus or what? And then when you, this is table 4b. Table 4b, I usually do this. Say when I go that way, it is what? Can you see Mg here? It is Mg0, and then it goes to that side, it is Mg2 plus. So if it is Mg2 plus in this side, can you see that oxidation occurs? Remember, oxidation, it is an increase in oxidation number. Oxidation number increased from 0 to 2. So this one, it is oxidation. And then it means this one here, reduction. Why? Because C2 plus to Cu0, there was a reduction in what? In oxidation number, a reduced in oxidation number. So this is reduction. So which one? This one, can you see it goes from this point to that one? So we're gonna write it as Mg forming Mg2 plus 2 electrons. And then this one, we're gonna just write it exactly as it is, with one arrow, guys, with one arrow. So can you see we want to know which one releases electrons? Which one releases electrons? Therefore, can you see that we realize that Mg is the one that releases electrons? Okay, we saw that Mg is the one that releases electrons, and this one, copper acquires electrons to form what? To form as pure copper. This is what we saw from this part, from my analyzation thereof, of my table 4b. Okay, when I go there, when I use my C method, okay, yes. So Mg forming, you don't write it like this. It's accepted, but it's weird, guys. Just write it from here to there. Just know it is Mg, then to Mg2 plus and that. Okay, so yes, guys. So, and I know that each cell should have the its whatever thing here, ions. So this one will have magnesium sulfate ions. Okay, magnesium sulfate ions here, and then this one will be copper sulfate ions, not copper carbon, sodium carbon, carbonate, no, not sodium carbonate, you don't use this one. So this is it, guys. And then let's see. I think we have labeled here. I needed just to say it is Mg. This one is pure copper. Okay, these are just there. Or on another thing in here, oxidation, in here, reduction. Okay, occurs. And then remember, how do electrons or the ions move? The ions move. Remember this one. This is a reduction, and remember a reduction, it is positive. Again, this cat, okay, red cat, and then an ox. So this is the anode. This is the anode and the cathode. Okay, so what's gonna happen is that since well this one has now is releasing 2 minus, we will try to neutralize those 2 minus by taking what, SO4 2 minus from this point to that side, and then this one, since well it becomes more negative, we are trying to balance it with more positives, okay? So we will release more positives to that side. So we are trying to balance the cell neutrality. And then write down the balanced equation for half reaction taking place at the cathode. Cathode, here is the cathode, guys. Here is the cathode. So I'm just going to rewrite that to be copper 2 plus 2 electrons forming me copper. Okay. You use double arrow, guys, you forfeit 1 mark. Calculate the initial EMF of the cell. Okay, I know that for me to calculate the initial EMF, it's easy, guys. This is easy max. E naught of the cell, it is equal to E naught of reduction. Not reduction, you have to write it in full. Actually, we say E naught of the cathode minus E naught of the anode. Okay, even if you write reduction or uh, you can say, okay, oxidation is still fine, still acceptable. Then the cathode, remember it is what? The cathode, remember it is a copper, and copper has this one of 0.34 minus anode. My anode, it is this one, Mg, and Mg from the standard of reduction, it is negative 2.36. Guys, we can confirm that if you don't believe me. Negative 2.36 as well as 0.34. And then we just need to just do basic mathematics, then this will be 2.7 volts. And then state one function of the salt bridge. The salt bridge completes the circuit, ensures cell neutrality. Again, it maintains the electrical neutrality, and then separate the two half cells. So these are 3 possible answers: this one, or this one. Okay. Sorry. How will the following change affect the initial EMF? Right only increase, decrease, or remain the same. The concentration of Mg2 plus is increased. Well, on this one, you will need the what is this? The net ionic charge. Okay, so the net is gonna be you're gonna add this to this one again. So it's gonna be, let me edit, Mg2 plus 2 electrons. Okay, I think I'm making a mistake here. Okay, so we have Mg to form Mg2 plus, then I add it to copper 2 plus 2 electrons forming me copper, and then the net is gonna result to being this and this cancel, remember, Mg plus CO2 plus Mg2 plus CO. Okay, just CO. This is the net. So the question is, what will happen if I increase the what? The concentration of Mg2 plus. Can you see if I increase the concentration of Mg2 plus, Le Chatelier's principle applies here. We're gonna favor the what? The reverse reaction. And when I favor the reverse reaction, now what will happen? The EMF will decrease. Okay, because the EMF supports the forward reaction. Okay, the EMF is produced when we are going forward. Okay, then we get more reading. But when we choose the reverse, therefore it means our EMF will do what? Will decrease. The area of the copper is increased. The area of the copper is increased. Well, when I increase the area of the copper, then that does not necessarily change anything, because now why? Because it means now copper will move just freely, not necessarily having an effect on the what? On the EMF, because yeah, I mean surface area. I mean, so it's gonna remain the same. So that's basically that for that one. And then question 9, I think I'm gonna do it same time. Electrolyte. What is an electrolyte? Let me see if I will have enough time to do it. Okay, I think I will. What is an electrolyte? A substance that whose aqueous solution contains ions, or a substance that dissolves in water to form solution that conducts electricity, or a substance that conducts electricity through the movement of ions. This is one of the definitions. Okay, I think we did not read that. Impure copper is refined. Okay, remember, if impure copper is refined, so here we have negative and positive. So this one is the negative terminal, positive terminal. And remember, on electrolytic, negative it is cathode, and then positive it is anode. And every time when we are trying to purify something, we're gonna purify anything. Whether I'm trying to purify something, I'm gonna purify it on the cathode, and then the impurities will be on the anode. So the impurities, impure will be here, and then the pure that I'm trying to find will be in here. And then name a suitable solution that can be used as an electrolyte. Okay, as an electrolyte. Well, you can use as an electrolyte, you can use what we refer to as copper sulfate. Okay, you can use copper sulfate, guys, because you have copper here. It's easy, just check you have what copper, and then you can say the name, guys. They say the name, so it's gonna be copper 2 sulfate. You need that 2. You need that 2 sulfate, or copper chloride. Okay, or copper 2 chloride, or any type of chloride with any solution, except for what? You have to except for, what is this? Silver. Because why? Because silver will do this. What will silver do? It will form a precipitate. Okay, but yeah, between these two, you can choose between these two. And then, okay, this is 2, guys, sulfate. Write down the equation of the half reaction that takes place in at the anode. At the anode here, guys, at the anode, remember we are trying to do what? We are trying to, okay, and another thing, guys, a hint is that electrons will move from here to there. So it means it will be copper moving to what? 2 plus 2. Let me do this. It's going to be copper releasing electrons. How can it release electrons like this? Because electrons move from here to there. Can you see? This is negative, this is positive. So they're going to move from there to there. So this is the half thingy, guys, that occurs at the anode. Don't need to gram it, just know it. And then they tell us a precious metal such as silver, which is usually part of the impure anode, sinks to the bottom of the cell. Explain this observation referring to the reduction relative strength of the reduction agent. Now they're basically saying why in these impurities this will be pure copper. Why in these impurities did they manage to purify copper instead of silver? Okay, so remember this is the cathode, so it undergoes reduction. Okay, so it means the one that underwent reduction. So it means copper has a stronger reduction, has a stronger oxidizing, is a stronger. Agiri, copper is the one that underwent reduction, so it was reduced. So it means copper is a stronger reducing agent than silver. Because if silver was a stronger reducing agent, it was the one that was going to undergo reduction. Okay, so you can say uh, copper is a stronger reducing agent mhm, than silver. Okay, and silver will not be done what? Will not be oxidized. I'll explain that. If I check here, I have this one or Ag to Ag plus electron, but I can go to my tables. Okay, I go to my table and compare between Cu as well as Ag. Where's Ag? Where's Ag? Where's Ag? Where's Ag? Quickly, Ag is here. So if I were to look at the copper here and Ag, can you see reducing ability? So the one that can go oxidation faster is which one? Can you see? It is Cu. Cu, it is a stronger reducing agent than Ag. So hence now Cu is the one that will undergo a oxidation. Okay, it will undergo what? Oxidation here at an anode and form what? Cathode, pure copper on the cathode. Okay, yeah guys, it's just easy. You just need to say is a stronger reducing agent than silver and this one will not be oxidized. And then the last question says, after 10 minutes, 1.6 grams of pure copper is deposited on the electrode. Okay, we have mass of copper. Calculate the number of electrons that flows through that flowed through the circuit while the mass of copper was deposited. Okay, okay. Now let's find the number of moles of copper because we have the mass of copper. Number of moles of copper is gonna be mass divided by molar mass. They want the what? Electrons that flowed. Okay. So let's find number of moles because number of moles can help us get anything. Molar mass of copper, guys, it is 63.5. Then the number of moles of copper is going to be 0.02519. Allow me to keep those all decimals. And then, since well now, uh, copper, since well one copper atom gives, let me say, since one copper atom gives off 2 electrons. It means therefore number of moles of electrons, okay, is gonna be double, or yeah, it's gonna be double. Let me do the ratio. 1 is to 2 because it gives off 2. Can you see? I want you to see. Can you see it is 1 is to 2? So if this one it is that one, then X, which is number of moles of electrons, is gonna be twice that, which is something like 0.50, 0.5039 moles. And then I can get number of electrons. Okay, how do I get number of electrons? Well, number of electrons n divided by Avogadro's constant, where this is number of particles. And remember, particles include atoms, electrons, molecules, and all of that. So I have number of electrons to be how much? To be um, 0.05039, then n, which is number of electrons that I'm looking for, divided by Avogadro's constant is 6.02 times 10 to the power of 23, and then n is going to be now 3.034 times 10 to the power of 22 what? Electrons. So that's basically that, guys. Find number of moles using copper and then use the mole ratio between copper and electrons, and then use Avogadro's constant equation to find what? The number of of electrons, okay, found in the number of particles thereof. So yeah, guys, that's, am I missing any question? I don't think so. Yeah, I think everything is fine, guys. Everything is fine now. So yeah, hopefully you enjoyed the question paper from Gauteng thereof. Those who were writing it, hopefully it wasn't that bad. Those who are practicing using it, hopefully you did not find more difficulties. Thank you.